Hello everyone, my name is Jinru Yi. I come from Rutgers University. Today I'm very glad to introduce my work, Oriented Object Detection in Aerial Images with Box Boundary Aware Vectors. Object detection in aerial images serves as an essential step for numerous applications, such as urban planning, traffic surveillance, port management, and maritime rescue. Objects are usually densely packed and displayed in arbitrary directions. Consequently, applying the horizontal bounding boxes to oriented object detection would lead to misalignment between the detected bounding boxes and the objects. To deal with this problem, oriented bounding boxes are preferred for capturing objects in aerial images. The object detection can be divided into two types: the anchor-based object detection and anchor-free object detection. Anchor-based object detection methods generally spread anchor boxes on the feature maps and predict the offset between the output box parameters and the anchor box parameters. The key point-based object detectors show advantages over the anchor-based ones in terms of speed and accuracy. Yet, the key point-based detectors are barely applied to oriented object detection tasks. In this work, we extend Joe's center net to the oriented object detection. Joe's center net suggests detecting the object center and regressing the width and height of the bounding boxes directly, which achieves faster speed and comparable accuracy. Intuitively, Joe's center net can be extended to the oriented object detection by learning an additional angle theta together with W and H, as shown in Figure 1. However, as the parameters W and H are measured in different rotating coordinate systems for each arbitrarily oriented object, jointly learning those parameters may be challenged for the model. In this work, we learn the box boundary aware vectors as shown in Figure 1b to capture the rotational bounding boxes. The vectors, we call them as BBA vectors, are distributed in the four quadrants of the coordinate system. In practice, we observe in the corner cases as shown in Figure 1c, where the vectors are very close to the boundary of the quadrants. It would be difficult for a network to differentiate the vector types. To deal with this problem, we group the oriented bounding boxes into two categories and handle them separately. Specifically, we have two types of boxes: horizontal bounding boxes HBB and the rotational bounding boxes RBB. This figure shows the overview of our network. We use the ResNet 101 as the backbone. The output has four channels. The first one is heat map, which is used to predict the possibility of the center points of the objects. The heat map and offset are used to decode the center point of the object. The box parameters predict the BBA vectors and the external width and height of the oriented bounding boxes. We compare the performances of the proposed BBA vectors plus R and the BBA vectors plus RH to start the impact orientation classification. We evaluate our methods on two datasets, the DOTA and HRSC, where DOTA contains very large resolution of images. So we have to split the images first and then merge the results together. We resize the input images to 206 times 206 in the training and testing stage, giving an output resolution of 152 times 152. We implement our method with PyTorch. We additionally report an experiment with large batch size 48 on 4 NVIDIA Quadro RTX 6000 GPU. The red color labels the results with a large batch size. Compared with the blue color, it can be seen the large batch size would improve the results by a large margin. Compared with the baseline method, the BBA vectors achieves better performances. In this paper, we extend the center key point-based object detector to the oriented object detection task. If you have any questions, you can send me email or discuss in the GitHub. Thank you.